Okay, we're going to do chapter 2, problem 27. This is on page 60 of your book. And the problem says, a car traveling at 30 miles per hour runs out of gas while traveling up a 10-degree slope. How far up the hill will it coast before starting to roll back down? Okay, so let's start out with what are we given? Okay, our given is that the slope is equal to 10 degrees. Okay, our initial velocity is equal to 30 meters per second. And our final velocity, of course, will be 0 because it's going to stop and then it's going to roll back down. And then we're supposed to find how high does it go. So we'll call that delta x. Okay. So our solution, let's start out by drawing a picture. So we have a slope. It's at approximately 10 degrees. And then we have a car that's driving up this slope. And again, all my cars look like Volkswagen Bugs. So it's going up the slope, and all of a sudden it stalls, I think it said, right? Runs out of gas. Yeah, so basically it stalls. So it's going to go up for a little while and then go back down. If we want to draw a diagram of this, it's going to have a high velocity here, and then it's going to decrease. And then eventually it's going to go back down. But we're just concerned about the part where it's going up. So our initial velocity, so this would be v1, v2, v3, v4, and then v5. And of course, in this case, that's going to be equal to 0, and this is going to be equal to 30 meters per second. Okay. Now, when we did problems before, we were looking at vertical motion, things going up and down. In this case, we're going to have something going up a slope. So we're going to use an equation, 2-26, and that has that the acceleration is equal to minus g times sine theta, where theta is the slope. And g, of course, is still the acceleration due to gravity. Where this comes from is if you were to draw an arrow showing where gravity is, right? And we'll get into this a little bit, but I'm going to put my g on the other side. This means gravity has a component that points down the slope and a component that points perpendicular to the slope. And so this is the one that we're concerned with. And we'll get into the explanation for this when we get into forces and things like that. But just so you know, that's where it comes from. So how are we going to solve this? Well, we're going to use our kinematic equation, but remember I said we don't always use g for acceleration. In this case, we're going to use g sine theta for acceleration. So we're going to, since we're looking for distance, the one that works the best is v final squared equals v initial squared plus 2 times a times delta x, or delta s in the book. In this case, our final velocity is equal to 0. So we know a, we know g, so I'm going to kind of substitute things in. We have our initial squared plus 2. Now I'm going to go ahead and throw in that minus g sine theta delta x. Okay? We're going to solve for delta x. So that means we're going to move vi squared over, well, we're going to have minus 2g sine theta. That will be equal to delta x, and then our signs cancel. So delta x is equal to 30 meters per second quantity squared times 2 times 9.8 meters per second squared times sine of 10 degrees. Okay, and when I plug all those numbers in, we should be getting something like 264 meters.